Welcome to the final video of the behavior demo. Up to this point, we have created a behavior system and a series of behaviors to test the system. Now in this video, we're going to wrap things up by just throwing together a few example scenes where we've got all of our behaviors that we wanted to test fully in place. So all we're going to do in this video is use those behaviors and some additional actors to create some more interesting scenarios. So what we're going to do is two different scenarios. One, we're going to use the avoidance behavior to create a wall around the entire viewable area to kind of pin all of the actors in so they don't wander off screen and screen warp as often. And we're also going to see how the behaviors of avoidance and seek can be combined to make an enemy actor. An actor that both moves on its own and carries the avoidance behavior so that the other actors will avoid that enemy. So to get started, let's take a look at putting some border walls around the entire scene. We've already got a scenario set up with this obstacles list that will allow us to create any number of obstacles, and then all of those obstacles will be respected by the other actors. So what we're going to do is we'll jump in here right after the existing 4 obstacles get created, and we're going to write some code that will allow us to very quickly place a line of obstacles at the top, bottom, right, or left of the screen. We'll apply all of these directions, and then we'll get a square or rectangle of obstacle actors placed around the visible border. Now we're going to make 2 variables to describe the size of this rectangle. We're going to have a count in the horizontal direction and a count in the vertical direction, saying how many actors we have, how many obstacles we have vertically and how many obstacles we have horizontally. So to begin with, we'll have an integer that we're going to call h count. This will be our horizontal count. And for this variable, I'm going to create a value. I'm going to initialize it using the value screen width divided by 100. Because if you think about it, we've got a screen width currently of 800. If we divide 800 by 100, that will result in a count of 8. If we evenly space actors, if we evenly space 8 actors across a screen, we should end up with a spacing of 100 pixels between each actor, totaling a value of 800 and filling out the screen. We'll do the same thing for the vertical direction. We'll make an integer called vCount. And let me change the capitalization on count. And that will be equal to screen height divided by 100, giving us a value, if we look at our current screen height, which is set to 600, divided by 100 will give us a vCount of 6. Alright, now we need to create a series of obstacles across one of the borders or edges of the screen. Let's begin with the top edge of the screen. We'll make a for loop that will drop in a number of actors equal to h count. So creating a for loop, we'll hit tab, leave the index variable set to I, and the length set to h count. Now as we're going through count by count, we need to make new obstacle actors and position them. So inside of the loop, we'll make a local actor variable. We'll call this variable obstacle, and set it to be equal to a new instance of actor. To make a new actor instance, we need to pass in the arrow texture and a specific color. Here we'll simply drop in obstacle color. So that will take care of the instantiation of a new obstacle. Now we need to set the obstacle's position. So obstacle.position will be set based on the index variable and where we are on the screen. We'll use hCount to figure out what percentage of the screen we've covered so far. So position, well, to begin with, we're going to need a vector 2 in order to assign this. So we'll assemble a new vector 2. Now we'll be positioning these horizontally, so it's the x component that we're interested in. What we want to do is we want to find the percentage that we are throughout the loop, meaning we start at 0 and we progress all the way up to 1 before 8, giving us 8 total objects. If we divide I against h count here inside of the loop, that will provide a percentage. So that way if we reach halfway into the loop, we'll be at 0.5. This percentage is useful because we can multiply it by the screen width and give ourselves a position based on that percentage. Now, of course, in order to get a decimal percentage, we will need to cast one of these operands over to a float. So what we'll do is we'll cast the index variable I to a float and then divide that against the total number of iterations of the loop given by h count. So that will give us a percentage. So looking at this expression here, that will give us a decimal percentage and a value of 0 to 1 as to how far we are into the loop. We can take that value and multiply it against screen width, and then that will evenly position these actors across the total width of the screen. So with that, we can drop in a comma to indicate the end of the x component. Now we need to specify the y component of our vector 2, and I'm simply going to drop in 0, since we'll be placing these obstacles at the top of the screen. We can finish off the creation of the vector 2 and terminate the statement for our position. Now for our direction, we'll simply assign a direction so that we can have our obstacle actors pointing down. So what we'll do is, as we're creating a border of obstacles, we'll have them point inwards towards the center of the screen. So what we'll do with the top line of obstacles is we'll point them down to the bottom of the screen. So obstacle.direction will be set to a new vector 2 with a value of 0 in x and 1 in y. Alright, now that we've got the new obstacle actor created, we do need to remember to place that into the obstacles list. So we'll say obstacles.add, and we'll drop in the current obstacle variable. Alright, with all of this assembled, let's build and run the game and make sure that we have a line of obstacle actors up at the top of the screen. So jumping in here to the game, we can see that we have the points of those obstacle actors all at the top of the screen. And every so often you'll see some of the actors getting close to those, and they avoid the entire top edge of the screen now. You will notice, because we don't actually reach the 8th value in that loop, we're not placing an actor at the very edge of the screen. It's almost like we have an empty slot where the next actor should go. We're going to leave this behavior in place so that each edge can be drawn with the same calculation in mind. What that means is this ending obstacle actor will actually be drawn as the first in the vertical series, and then so on. It's almost like a rough way to explain that would be the overlapping edges of a cardboard box. We'll have each edge overlap a little bit, and that way we can do the same calculation, instead of, for example, squashing the vertical lines inside of the horizontal lines. So now that we know that our code is working for the top line of obstacles, let's assemble the bottom line of obstacles. This will be relatively easy, since we can copy the existing for loop and simply change the y position. Now, since we're going to get a lot of similar looking code, I'm going to drop in comments by each of these loops to indicate which row of actors they create. So the first loop is going to be generating the top obstacles. The second loop is going to be for generating the bottom obstacles. Now, the things we need to change are 1, the position. Our y position needs to be the bottom of the screen, so we'll simply drop in the value of screen height. Now currently these obstacles are facing down in y. We'll change this to -1 so that they face up in y. Now if we run the game, we'll see that they do exist here at the bottom of the screen, but if we're following the mentality of drawing the actors as though we're moving, starting at the top left, moving to the top right, then we want to move from the top right to the bottom right, we actually want to begin drawing these actors here over on the bottom right of the screen, not the bottom left. So we want to start in this corner and begin drawing so that our gap appears on this side of the screen. To do that, we could simply invert the direction that we're drawing here. As we're dropping these here in x, what we could do is keep this existing calculation and simply subtract it from the screen width. So we could say screen width minus the calculation for our individual obstacles. So that way we start on the right side of the screen and move to the left. So what that results in is now we have, it's almost like a shift. We've moved over to the bottom right of the screen, leaving the area open here on the left. Now let's take a look at drawing our vertical obstacles. So we'll begin with the, let's start with our first loop. Let's grab the top loop, paste it in after the bottom loop, and rename the comment to right. Now inside of the right direction, we need to change the axis along which we're creating actors. Here we're currently creating them along the X component. We need to do this along the Y component. So what I'll do is I'll drop in, let's see, we'll drop in a new value for X. We'll drop in screen width for X, drop in a comment to move on to our Y, and then scroll over and make sure we remember to erase that additional 0. So if we bring up the parameters list, we can see that for a value of X, we have screen width, which will of course drop us on the right-hand side of the screen, and for a value of Y, we will advance based on our count. Now that's the next point of interest. The count is currently the horizontal count, and in this case we want to loop across the vertical count. So inside of our loop here, we'll change this to vCount, make sure we divide I against vCount, then make sure that we multiply this value against the screen height. And that way we'll evenly fill out the height rather than the width. Now as for our direction, let's cause each of these obstacles, since they're on the right-hand side of the screen, to point to the left. So we'll give a value of -1 in X and 0 in Y. Now if we build and run the game, we should see a series of obstacles being positioned across the right-hand side of the screen. And now you can start to see where the spacing slot fits. So starting at the top left, we have evenly spaced actors all the way across the top, right, and bottom of the screen. So all that remains now is the left of the screen. To create the loop for the left of the screen, let's take our loop currently generating the right-hand edge, copy and paste to duplicate it. Make sure our comment indicates that we are drawing the left-hand edge of the screen. Now inside of our obstacles positioning, instead of screen width, we will specify a value of 0. So that way 0 and X will position us on the left-hand side of the screen. Now in order to fill out that slot on the very bottom, we need to start at the bottom. So we'll give ourselves a value of screen height, and then we'll subtract the values that we find by running our I against count times screen height calculation. So let's build and run the game. We see that we do have the actors positioned, though we still need to update the direction. They're still facing off to the left. Here we'd like them to face to the right. So very briefly, we'll jump into code and change this -X, -1 to +1 in X, pointing us to the right, and giving us our final set of obstacles. So now we have all 4 edges of the screen bounded by obstacles, and now if you watch the leader actor, as he gets close to the edge, any edge of the screen, he turns around to face away from it. Now you will find specific exceptions where the leader still manages to make it through the obstacles and screen warp. The reason is if he's facing, let's say, directly to the x-axis, so directly right, and he faces an obstacle facing exactly to the left, he'll probably be able to make it through it, since it will take him too long to fully turn around, since the vectors are almost opposing each other. So the constantly renormalized vectors will give him a slow rotation in that case. So like he just did on screen, he warped over to the other side of the screen. But generally watching the actors, they are now bounded by all the actors along the edge. And again, all of this was put together just to show that we can now put together a more complex scenario by using our existing actors almost as primitives. So rather than always coding in specific scenarios, we can take a relatively general set of classes and apply them to different scenarios. Alright, now that we've seen how the obstacles can be used to make things, in addition to simply creating point obstacles, we can make entire boundaries. Let's take a look at combining the avoidance behavior with a moving actor, because up till now, we've only used avoidance with stationary obstacles. Let's create the idea of an enemy. Let's make a moving actor that follows the leader actor, but is set up in such a way that all of the other drone actors do not like the enemy. Let's set them up to avoid the enemy. Now, in order to put this together, let's scroll down to our leader's creation. We'll jump in here right after the leader, and we can define an enemy. In addition to this enemy, in order to get a clearer view of what's going on, I do want to temporarily remove the center for obstacles. We want to, for the time being, just focus on this enemy style of behavior. So what we'll do is we'll take the 4 obstacles that we're creating with this for loop and manual assignment, and we'll comment this block of code. And again, this way we can focus on just the enemy itself. All right, moving back here to our leader definition. Right after our leader definition, let's make an enemy. We'll make an actor variable. We'll call that actor enemy, and we will instantiate a new actor. We'll use the same arrow texture for our texture, and we want a red color for the color parameter. So we'll make a new color. We'll give ourselves a value of 255 in red, 120 in green, and 120 in blue. Then we can finish off the call to our new actor. So we have our enemy defined. Let's set up some of the additional fields on this enemy. Let's say that the enemy's speed is set to a value of 3. This will be equal to the speed of all of our drones. Actually, we could possibly test at 3. Just to make it a little bit more clear, it would be nice if we could see our drone cloud move across the enemy more often. Let's actually slow the enemy down a little bit. Meaning if the enemy happens to be close to the leader, the drones will be able to speed up and catch it, and then we'll get to see them fly around the enemy as they move closer to the leader. All right, we need to set up a position for the enemy. So we could use a random position, but just to make it easier to test the scenario, let's have them all start off on at a specific position on the screen. It'll just make it a little bit more reproducible as we launch the game. So we'll take our enemy's position, and we'll set that to a new vector2 with values of 200 in X and 150 in Y. All right, with our enemy, let's give this enemy a few behaviors. Let's have him, of course, seek after the leader, but also wander. So the idea is that he will, instead of being a perfect, smooth seek, we'll have him wander a little bit on his own. So let's begin with the wandering behavior. We'll take our enemy, look at his behavior list, we'll add a behavior. That behavior will be a new behavior wander. And the properties of this wandering behavior will be a weight of 0.1 and a change interval of 30. So every 30 frames, we'll pick a new direction. Then we can close off the parenthesis for our behavior add, and we're ready to add a second behavior. So again, looking at enemy's behavior list, we will add, this time, a new behavior seek. For our behavior seek, we'll give a value of 0.1 as our weight, and we will specify the target actor as the leader. Then we can close off the parentheses for adding in our new behavior. And you'll notice that the weights on these are equal. So we'll have equal amount of wanting to move or wander in a random direction and wanting to seek after the leader. Now, in order to count this enemy as an obstacle, what we'll do is we'll jump in here inside of our drones, and right before we set up all the obstacle avoidance, let's set up enemy avoidance. What we'll do is we'll put the avoid behavior on each of the drones. Now before we create this behavior, rather than instantiating it here inside of the for loop, since we're all the drones are going to be avoiding the same obstacle, we could create an avoid behavior and then apply that same behavior to all of the drones. So again, just like we did with the seek, we'll set up a scenario where we reuse a single behavior. So we can make a behavior variable. Let's call this behavior avoid enemy. And then we will set up a new behavior avoid. We'll give ourselves a value of 0.2 for our weight. We will avoid the enemy actor, and we will avoid with a radius of 120. So we'll actually try and stay farther away from the enemy than we will from various obstacles. Now when we're looking at individual drones, we'll take those drones, we will add to their behavior list that avoid enemy behavior instance. So now all of the enemies should want to avoid, or excuse me, all of the drones should want to avoid the enemy with the same parameters. So let's jump into the game and test things out. So let me take control of the leader actor and start moving him around in a circle. So you can see we have this new red actor. He is trying to follow the leader. He's doing so a little bit more sporadically, though. You can see that his wandering and wandering and seeking are evenly balanced, and all of the drone actors are maintaining a rather wide radius around him. So if I try to, as the leader, stay near the enemy, then all of the drones will have trouble following the leader, because every time they hit that drone actor, they split and avoid around it. So, with this now in place, let's go back to code very briefly, and just for the fun of it, let's try upping the number of drones. Let's jump up to 100 drones. So with a larger flock of drones, it's even easier to see the radius around that enemy. You can almost visualize the circle where all of the drones are trying to avoid that enemy. Plus, you get a lot of neat visual results as we slide past the enemy and see a wide flock of drones all splitting to try and avoid that one enemy. You also get some interesting movement patterns as that number of drones tries to follow the leader. So you get some interesting turning parameters. Now, one last thing we can do is let's put those original obstacles back in place. So we can have both an enemy and some center obstacles. So we can drop these in place. Now we have 100 drones, lots of obstacles, and an enemy. So lots of things that are trying to be avoided. At this point, you start to lose the motion of individual drones, and you just see the wave motion patterns of the many drones avoiding multiple things. Then just to wrap up the demo to its final state, let me take the number of actors back to 10, and then we can see all of the intended elements. So now we have a scene combining many different aspects. We have a core set of behaviors, we have a set of obstacles, and drones, and all these objects are now interacting with each other. Their interactions are described by the various behaviors. So with that, we've now reached all the topics that we needed to cover inside of this demo. We've started off with the simple concept of an actor model. That is, we had a simple scene with multiple actors. Each actor moved based on its own direction and speed. We then enhanced this model by allowing each of our actors to have any number of behaviors. These behaviors would describe the direction that the actors moved in. Having created this behavior system, we were able to code a number of behaviors, from things as simple as moving in a continuous direction to doing a radius-based avoidance. Now, with all of these, that was interesting, but we'll take a look at that in just a second. But again, just to finish things off here with this, we've got the ability now to describe more complex movement patterns based on some primitives. I mean, you can almost say conceptual behavior primitives. So with that, having accomplished all of these different topics, put them all together into a coherent scene, that is going to take care of this video. And just one quick note, but since we're ending everything off here, what was happening with everything disappearing is most likely somehow we resulted in a value of 0 getting normalized for our leader actor. So since he disappeared off screen, what ended up happening is our float values for the vector ended up getting set to not a number. So to debug that, what we would need to do is to go find every place that the leader is being set and making sure that our directions are always getting normalized. Things like that would include sections here where we're taking directions and directly normalizing them. So what would happen in these cases is, let's say we had an actor and a target that managed to get to an identical position. Let's say they were both at 0, 0. We would then have a length of 0. We would get in here because 0 is less than the radius, and we would try to normalize the 0 value. And if you think about that, if you have a vector with 0 length, where is he pointing? You can't define where that vector is pointing, so you end up with a result of not a number. And to draw a not a number to a screen, that doesn't have a pixel value, so you don't draw it anywhere. So again, to avoid the problem of everything randomly disappearing, we would need to be very careful in each of our definitions, making sure that we check them before we normalize them, and then we would safely have the scene progress indefinitely. So with that, having covered the topic of actors, behaviors, layered behaviors, and scene setup, that is going to wrap up this video, and that is also going to wrap up the actor behavior demo.